Hello everyone. This is part one of a review for exam 3. I thought maybe it would be nice to review just like we would in a classroom, so I'm going to guide you through some of the review examples. So this document is posted in Blackboard under the handout section, and it's your review for the exam. There's 2 pages, and then there's the answers posted in a separate document. What I did was I basically just took that document and gave myself some room for specific questions, so I'm just jumping around, and we're going to go over some typical questions that you might expect to see on the exam. So first set of problems here, just basic partial derivatives using our different notation. And the first one we want to find, we'll do these 2 parts. There's more parts on the review. You can notice, that there's, in this question, there's these 4 parts, but I'm only going to do a few of each, and this will guide you through and show you what typical examples will look like. Concerning the partial derivatives themselves, be prepared for all types of functions. A lot of our more involved examples are just basic polynomials, but here I'm going to include some situations that involve other differentiation formulas. So if we want to find the partial with respect to x here, partial of f with respect to x, remember we're holding y as a constant, so this will require the formula for e to the u, so we just repeat e to the u. So e to the x squared y cubed, but then times the derivative of the power on the base of e. But y is being held as a constant, and the derivative of x squared is 2x, so therefore 2xy cubed. And maybe you would rewrite that, bringing the 2xy cubed out in front of the e to the x squared y cubed. So part B is similar, except now we're taking the partial with respect to y, and so x is going to be held as a constant, still the same formula, e to the u, so e to the x squared y cubed, but now differentiating the power x squared y cubed, where x is being held as a constant, we get the derivative of y cubed is 3y squared, so I'm going to write 3x squared y squared, and then again, if you want to bring the 3x squared y squared out in front of the e to make it look a little prettier, that's great. Okay, so then, so you're probably going to get like 3 questions, I think, worth 4 points apiece that are going to be similar to these first 4 examples. Just a basic partial, again, but different formulas. So for part A, the partial with respect to x, okay, that means y is held as a constant, so the derivative of sine is cosine of the same argument, 3x. Don't forget the derivative of the argument, so 3. So I'll put that in front, and then the y to the 4th cosine 3x. That's all there is to that one. And then for part B, partial with respect to y is going to be the derivative of y to the 4th, where x is held as a constant. That's 4y cubed. And the sine of 3x tags along as a constant. Okay, so moving on. Here we have a function of 3 variables. First off, partial of f with respect to x. Okay, so y and z are held as constants. So the z to the 3rd is going to tag along as a constant. But now we're differentiating the natural log of this quantity, where y is being held as a constant. So remember the formula, of course, for the natural log of u. We get a fraction, logarithm goes away. We put the argument, in this case, x to the 5th, y to the 4th, in the denominator of the fraction, and its derivative goes in the numerator, but we're taking the partial with respect to x, so the derivative of x to the 5th, 5x to the 4th, and the y to the 4th tags along as a constant. So for this one, in terms of simplification, probably cancel out the y to the fourths, as well as 4 factors of x. So we're going to have 5z cubed over x. And I think we'll find a similar situation for the partial of f with respect to y. That is, z and x are now constants. So the z cubed again is going to tag along, and we're going to need the formula for the natural log of u, which is fraction, log goes away, the x to the fifth, y to the fourth in the denominator, its derivative in the numerator, x being held as a constant, the derivative of y to the fourth is 4y cubed, so 4x to the fifth y cubed. And then simplifying that, we can cancel out the x's, 3 factors of y, so we'll have 4z cubed over y. And then finally for part C in this question, now the partial with respect to z. So this is where x and y are held as constants. So it turns out the natural log of this x to the fifth, y to the fourth is actually behaving as a constant, and all we're differentiating here is the z cubed. So that's 3z squared, and then times the natural log of the x to the fifth, y to the fourth that's being held as a constant. Okay, so then last example. So you can see we're entertaining a variety of different formulas here. Here, no matter what you're going to do, to begin with, you're going to want to get rid of the radical. So it's x squared minus y squared minus z squared to the 1/2. And now in part A, partial of f with respect to x. Okay, we're going to need the general power rule because it's a function raised to a power. Keep in mind it's with respect to x, so y and z are held as constants. So by the general power rule, we'll bring down the 1/2 times that same function, x squared minus y squared minus z squared, power 1 less than 1/2, negative 1/2, and then the derivative of what's inside. And so the derivative of the inside, again, we're doing it with respect to x, y and z are constants, so derivative of x squared, 2x, and the derivative of x squared and z squared are both 0. So then, making this look a little better, let's cancel the 2's, and we could bring this quantity, x squared minus y squared minus z squared to the denominator, now to the positive 1/2, and then I guess we're just left with an x in the numerator. Okay, and then similarly for part B, partial of f with respect to y. Same formula, still going to be general power, chain, u to the n, whatever you like to call it. And we're going to bring down the 1/2, but now we're doing it with respect to y. So that same quantity, x squared minus y squared minus z squared, power 1 less, negative 1/2, derivative of the inside, x and z are constants, so their derivatives in this case are 0. Just be careful of the negative here. The derivative of negative y squared is going to be negative 2y. And so then we'll cancel out the 2's again, but be careful of that negative. In the numerator we have negative y, and then in the denominator the x squared minus y squared minus z squared, now to the positive 1/2. Okay, so I think there's like 3 questions where just find the partials, and that gives you a good variety of examples there. There's definitely a question, and I believe those are worth like 4 points apiece. Definitely a question like this, number 6 here, where we're asked to verify. Okay, so here we're asked to verify our formula here based on a given function. So we'll do each of these separately. So the second partial of z with respect to x. For the first partial of z with respect to x, we get, well, derivative, y is being held as a constant, so the derivative of e to the x is e to the x, and the sine of y as a constant tags along, but then the derivative of e to the y is 0 because y is a constant. So then the second partial of z with respect to x twice. So now looking at the partial with respect to x, do it with respect to x again, and derivative of e to the x, again, e to the x, and sine of y tags along as a constant. Oh, I'm sorry, I forgot this piece here. So going back to the first part, here's e to the y, then the cosine of x, derivative of cosine, minus sine, so minus e to the y sine of x, and back to the second partial now, derivative of sine is cosine, so minus the e to the y tags along with cosine x. Okay, so that's better. And now do the second partial of z with respect to y twice. So first partial with respect to y. Okay, now x is a constant, so e to the x tags along, and the derivative of sine of y is cosine y. And then the derivative of x is again a constant, so cosine of x is a constant, e to the y differentiates to be e to the y, so times cosine x. And then the second partial of z with respect to y twice. So looking at the partial of z with respect to y, do it again. And we have x is held as a constant, so derivative of cosine minus sine, so minus e to the x sine of y, and then plus the derivative of e to the y is e to the y, and the cosine of x tags along again. Alright, so now we substitute to verify, and here's the equation we want to verify. Just recopying it. And substituting, we have e to the x sine y minus e to the y cosine x. We'll make this plus bigger. So that's the second partial of z with respect to x, and then plus second partial of z with respect to y is minus e to the x sine of y, and then plus e to the y cosine x, and we want to know, is that equal to 0? And then by inspection you can see it is, because e to the x sine of y's cancel, and so do the e to the y's sine cosine x's. So 0 equals 0. And it's verified. Okay, so let's continue. Next page of notes. Up to number 7. We want to find the differential dz, which is where z is a function of x and y. And so you might recall that for these differentials we have a little diagram that sometimes helps us out to realize the formula. Little tree diagram here. If z is a function of x and y, then then the differential dz is going to be equal to the partial of z with respect to x times the differential dx, and then plus the partial of z with respect to y times the differential dy. So we just need the two partials. Partial z with respect to x. So let me do that off to the side here. I guess we really didn't need this. I'm sorry. I was thinking of the chain rule. So this is just by definition. So you're going to want to write that definition down on your cheat sheet. And doing the two partials off to the side, partial z with respect to x is derivative of x squared, 2x, derivative of y squared, y is a constant, so 0. Derivative of x cubed is 3x squared, y cubed tags along, so plus 3x squared, y cubed. And then I'll do the partial z with respect to y here. And now x is a constant, so we get derivative of negative y squared, negative 2y, and then plus derivative of y cubed is 3y squared, and the x cubed tags along, so 3x cubed y squared. So the differential dz is then the 2x plus 3x squared y cubed times the differential dx, and then plus negative 2y plus 3x cubed y squared times the differential dy. Okay, so now move on to number 8. Now we have a function of 3 variables, and the total differential dw then is again a definition. Partial w with respect to x times the differential dx plus partial w with respect to y times the differential dy, and then plus the partial w with respect to z times the differential dz. So again, I'll do the partials off to the side. Partial w with respect to x is, we have e to the xyz, so the formula e to the u, just recopy, e to the xyz, but then times the derivative of the power on the base of e, and we're taking the derivative with respect to x, so yz is a constant, or constants, derivative of x is 1, so that's just yz. So we get yz e to the xyz. Similarly, partial w with respect to y, recopy e to the xyz, but now y is a constant, so the derivative is xz. Probably put that in front again. And then similarly, partial w with respect to z again, recopy e to the xyz. Now, x and y are constants, derivative of z is 1, so times xy. Okay, and then just make sure you plug into the definition. And so we'll have yz, this is partial w with respect to x, yz e to the xyz times dx, plus partial w with respect to y, xz e to the xyz times dy, and then plus the partial w with respect to z, xy e to the xyz times the differential dz. So probably just one question on differentials, but make sure that you write down these definitions, 2 variable or 3 variable. Then the application of a differential, we have the radius and the height of a circular cone are 3 and 4 inches, with errors of at most plus or minus 0.01 inches and plus or minus 0.04 inches respectively. And we're going to use differentials to approximate the maximum error in the volume. So note that the formula for the cone is given, and basically we're told that the radius is measured to be 3 inches, the height is measured to be 4 inches, where the maximum error, which we refer to as the differential in the radius, is plus or minus 0.01, and the maximum error of the height, so the differential dH, plus or minus 0.04. Now the volume formula is going to come into play to calculate the partials, but by definition of differentials, the differential dV is going to be the partial of V with respect to R times the differential dr, and then plus the partial of V with respect to H times the differential dH. And I'll calculate the two to the side here. Partial V with respect to R. Okay, so now pi and H and 1/3 are all constants. Derivative of R squared is 2R. So we'll have 2/3 pi R H. And the partial V with respect to H, now 1/3 pi and H, or excuse me, 1/3 pi and R squared are the constants, and the derivative of H is 1, so that's just 1/3 pi R squared H. So then back to the differential. Okay, we'll plug them in terms of their variables. So here we'll have 2/3 pi R H times dr plus 1/3 pi R squared times dH. And then from here we'll just simply plug in the given values. So we'll leave the 2/3 and the pi. R was 3, H was 4, dr was plus or minus 0.01, and then plus 1/3 pi. R was 3, it has to be squared, and then times dH, which was plus or minus 0.04. So therefore dV would be, let's see, what do we get? Plus or minus 0.08 pi. Use a calculator if you wish. And then plus or minus, looks like 3.12 pi. So therefore the maximum error would be plus or minus 0.20 pi. Okay, so we'll stop the video here and we'll come back and continue with our review. Again, I'm not doing all the questions. You've got extra ones that you can practice and check on the review sheet, but hopefully you're finding this helpful.